Okay, so today's our topic is design of cylinder columns. Not many courses and subjects include the design of this kind of columns, but we are going to discuss this in detail. I will teach you both the sway frame columns and non-sway frame columns, but in this video you will be learning about the introduction about the cylinder columns, the difference between sway and non-sway frames, and the design of cylinder columns in the sway frames. Okay, and in the next video we will going for the design of cylinder columns in the non-sway frames. uh, let's start with the introduction. So it says that what is the difference between first order and second order analysis? A first order analysis is based on the initial geometry of the structure, assuming elastic behavior. Okay, so if a column is straight, you are considering it as straight, erect, and the load is applied on it the way you are assuming, and the column is behaving in an elastic manner. Okay, it is not, it has not entered into inelastic range. On the other hand, second order analysis considers the influence of lateral drift, number one, cracking, number two, member curvature, number three, shrinkage and creep on the forces in the structure. Okay, so all these phenomena are included in the second order analysis. So this is the difference between first order and second order analysis. Now, what is the difference between sway and non-sway frames? The non-sway frames are the structural frames whose joints are restrained against lateral displacement by attachment to rigid elements or bracing are called non-sway frames. For example, in the figure you can see there is a shear wall. This is the shear wall and it is too stiff against the applied load, so that all these joints, they do not have any lateral displacement. Okay, and they are restrained in the lateral direction because of this shear wall. And according to ACI 31814, a column in a structure is non-sway if the increase in column moments due to second order effects does not exceed 5% of the first order end moments. Okay, so if the second order movements are less than 5% of the first order movements, then it is a non-sway frame. Okay, and the column is a non-sway column. Moreover, ACI code also says assumes a story within a structure is non-sway if Q is equal to summation of PU delta naught divided by VUS into LC is less than or equal to 0.05. Okay, if this Q is less than or equal to 5%, where Q is the stability index, which is the ratio of secondary movement due to lateral displacement and primary movement, which is exactly the equation representation of this statement. Okay, where Q is a stability index and it is the ratio of second to primary movement. Summation of PU is a total factored vertical load in the story. VUS is the factored horizontal story shear. LC is the length of column measured center to center of the joints, and delta naught is the first order relative deflection between the top and bottom of that story due to the shear story shear. Okay, so this is how you determine the factor Q, which is stability index, and then you say that whether it is a sway frame or a non-sway frame. On the other hand, sway frames are the structural frames not attached to an effective bracing system but depend on the bending stiffness of the columns and girders to provide resistance to lateral displacement are called sway frames. For example, all the frames you have been learning in your PRC1, PRC2, structural analysis 1, 2, they were all sway frames. Okay, and of course when you apply a lateral force, they will deflect and deform in a new shape, and they will resist the applied force with the bending stiffness of the columns and girders and the joints. What is this? You will learn in the slides to come. For the non-sway frame you can see a graph, and for the sway frame you can see a graph. A is for non-sway and V is for the sway frames. Okay, the K factor, you know about the K factor, you have learned them in the mechanics subject. To determine the K factor, you need to know psi A and psi B for both kind of frames. Now, effective length factor K, which I showed you on the previous slide of columns of rigid frames. The effective length of column is the length of a column hinged at both ends and having the same buckling load as the column being considered. Okay. Thus, the effective length factor K is the ratio of the effective length to the original length of the column. And for the column hinged at both ends, the effective length K is equal to 1. The ACI code recognizes the Jackson and Moreland alignment charts shown in figure below. Oh, it was figure above, not below. I put the slide before. To estimate the effective length factor K for a column of constant cross section in a multi-bay frame. Okay. The effective length factor K is a function of the relative stiffness at each end of the column. In these charts, K is determined as the intersection of a line joining the values of psi A and psi B at the two ends of the column A and B. The relative stiffness of the beams and columns at each end of the column psi is given by following equation. So psi is basically equal to summation of EC IC divided by IC whole divided by EBIB divided by IB, where you sorry, this is LC and LB. These are not I, this is LC and LB. Okay, so LC is the column length, LB is the beam length, EC column modulus elasticity, EB beam modulus elasticity. Basically, it is for the materials. IC is the cross-sectional property, right? Is the column moment of inertia, and IB is the beam moment of inertia. So with this formula, you will determine the psi factor. As an alternate to using alignment charts to determine K, the following simplified equations are used for computing the effective length factors for non-sway and sway frame members. For columns in non-sway frames, the smaller of the following two equations. Okay, so you get K by these two equations. Whichever is the smallest one will be used as a K. Instead of using these charts, you are using these equations, okay, where psi A and psi B are the values of psi at the two ends of the column, and psi minimum is the smaller of the two values. Okay, here you see psi minimum, this is the minimum of these two. For columns in sway frames restrained at both ends, K is taken as for psi m less than 2, K is equal to 20 minus psi m divided by 20 into under root 1 plus psi m, and for psi m greater than or equal to 2, K is equal to 0.9 into this value. So what is psi m? Psi m is the average of psi values at the two ends of the column. So you take psi A, you take psi B, you take their average, and this is psi m, which is mean value. Okay. For columns in sway frames hinged at one end, K is taken as K is equal to 2 plus 0.3 into psi, where this psi is the values at the restrained end of the column. Okay. This is, we are talking about sway frames hinged at one end. Okay. So please keep in mind. Now, what is the ACI procedure for classifying short and slender columns? According to ACI code, columns can be classified as short when their effective slenderness ratios satisfying the following criteria. For example, in non-sway frames, this factor should be less than or equal to 34 minus 12 into m1 divided by m2, and this value should be less than 40, and this value should be greater than this value. So this will be termed as short columns. Okay, and for sway frames, this value should be less than or equal to 22. Furthermore, compression members are considered braced against side sway when bracing elements have a total stiffness resisting lateral movement of that story of at least 12 times the gross stiffness of the columns within the story. Okay, so if the shear wall has the stiffness of 12 times to the gross stiffness of the columns, then it will be considered as a non-sway frame, where K is equal to effective length factor. This K, as you have learned on the previous slides, LU is the unsupported length of members defined in ACI section 10.10.11 as clear distance between floor slabs, beams, or other members capable of providing lateral support as shown. So in this case, this is your unbraced length. See, in this case, this is your unbraced length. However, in this case, your length from here to here is unbraced. Got it? So these were the different examples of how you will take LU, unsupported length. Continuing from the previous slide, uh, you have seen different things over here, right? K and LU are explained over here. You are left with the R, M1, M2. Okay. So what is R is the radius of gyration associated with axis about which bending occurs. Okay, so you know what is the radius of gyration. R is equal to under root I by A. You have learned these things in mechanics of solids very clearly. So I hope you guys know what it is and what are its uses. For rectangular cross sections, R is equal to 30% of H, and for circular sections, R is equal to 25% of H as specified by ACI code, where H is equal to column dimension in the direction of bending. Okay, so whatever the direction of bending is, for example, in a rectangular column, if one side is 18 inch and another one is 24, so most probably the column will bend about 18-inch side. Okay, so here you will take the H as 18 inches. However, in circular sections it is constant. M1 is the smaller factor and moment on columns. Positive if member is bent single curvature. Negative if bent in double curvature. Okay. So if it is bent about x-axis, you will take the value as positive. It is if it bends about x and y-axis, you will take it negative. M2 is a larger factor and moment on columns, and it is always positive whether it is single bent or double bent or double curvature. So chart on the next slide summarizes the process of column design as per the ACI 31814. So this is the chart that summarizes column design. You have to categorize whether it is in a sway frame or in a non-sway frame. You have equations and you have method to distinguish between sway frame and non-sway frames. Once you have calculated that your column is in, for example, let's say non-sway frame. Okay, so then come to the next step and check about the slenderness, whether it is a short column or a slender column. If it satisfies, then neglect the slenderness and design it as a short column. And you know how to design the short columns for concentric loads as well as the eccentric loading. Okay. However, if this condition does not govern and you are going for this condition, so for this condition you have to design it as a cylinder column and using moment magnification method, which we will be using in this lecture for the design of cylinder column. However, if this condition also does not prevail and it is going for this condition, the third one, then instead of using moment magnification method, you have to use exact p delta analysis, and of course you have to design it as a cylinder. And the same thing goes for the case of columns in the sway frame. Okay, now consider a frame with multiple bays in x direction, multiple bays in y direction, multiple story heights, and then you take a column. For example, the column highlighted in here, you have to design this column. Okay, so now consider the geometry and now consider the question what you have been asked. You have to design this column. The cylinder concrete column design in sway frame buildings. Evaluate cylinderness effect for columns in a sway frame multi-story reinforced concrete building by designing the first story exterior column. So this is the first story and this is the exterior column. Okay, this one is interior, this is interior, and this is exterior. The clear height of the first story is 13 feet and 4 inches. Now you know the clear height of this column, and is 10 feet 4 inch for all other stories. Okay, so these columns are 10 feet and 4 inch, and this column is 13 feet 4 inch. Lateral load effects on the buildings are governed by wind forces. Use ACI 31814. This is the cross-sectional details of the column. The column is a square column. You can see B is equal to 22 inches, H is equal to 22 inches. Okay, H by 2 is 11 inches. That is the uh, depth of this layer, the middle layer. So a total number of 8 bars, 3 2 3 three bars in first layer, two in middle layer, and three in last layer. So total number of number eight bars have been used. The effective depth from this phase is 19.62 inches, and effective depth for this layer is 2.38 inches. So all the basic requirements have been given to you, and you have been asked to design the cylinder columns. Now, the data concrete strength is 6000 psi for the bottom two stories columns and 4000 for the elsewhere. So our fc prime will be 6000, fy will be equal to 60,000 psi. Slab thickness is 7 inches, exterior columns 22 by 22, interior columns 24 by 24, beams are 24 by 20, and their span length is 24 feet. Superimposed dead load is 30 psf, roof live load is 30 psf, floor live load is 50 psf, wind loads computed according to ASCE 710. Total building loads in the first story from structural analysis are dead load 17,895 kp, live load 1991 kp, roof live loads are 270 kp, wind load is equal to 0 kp. Wind loads in the story cause compression in some columns and tension in others, and thus would cancel out. Okay. Okay, so starting with the first step, the service loads. On the exterior column service loads, you have different load cases: dead load, live load, roof live load, wind load, north south, and then south north. The axial load in kips on the column. So you have distributed the loads given to you on previous slide, and you have distributed it on each column. You are getting these types of loads. Okay, so wind flowing in north south direction is putting negative 48.3 kps. However, in the opposite direction putting 48.3 positive kps loads. Okay, so these both cancel each other in the absolute terms. So the bending moment in fit kip units at the top of the column, you are getting it. You can see the bending moments also cancelling out each other. Okay, so these are the service loads. Then putting different load combinations for the factored loads, we are using ASCE 710 for joining combining different loads. See, you got different kinds of loads here. You are putting them in different combinations. For example, 1.4 dead, 1.2 dead plus 1.6 live plus zero point 0.5 roof live, and all the other combinations. The references are provided here. The axial loads, the bending moments at top and bottom, then top moment in capes and bottom moments in capes, which you are going to use, and all these combinations give you different values of axial maximum axial load and maximum bending moments. Okay, so second step is checking slenderness effect and sway or non-sway frame designation. Okay, columns and stories in structures are considered as non-sway frame if the increase in column end moments due to second order effect does not exceed 5%. We already know this, and we learned that in the at the start of this lecture. The q index, we already know it, that it should not exceed 0.05. It's said by ACI 318. We know all these terms. Okay, from table 2, this is table 2. Okay, load combinations 2.3, 2.3.2 to 4, number 5 and 6 provide the greatest value of delta summation of pu. Okay, so summation of pu is equal to 1.2 dead plus zero point 0.5 live plus zero point 0.5 roof live. So this gives you 22,605 kips. Okay, and the reference is mentioned here. Vu as the shear, ultimate shear, is given by this equation, and delta naught is given by this equation. So you got these values, you know the equation, you just put the values in this equation, you know the column length. Okay, so the value is 0.12, which is much greater than 0.05. So The frame at the first story level is considered as sway frame, okay, and you have to consider the second order movements. Step number 3 is determining the slenderness effects. The you know the equation, right, in which you are using the k and I and l for the columns and beams. Okay, so starting right away with the column, the moment of inertia for the column is equal to 0.7 into c4 divided by 12. Now you know the dimensions of the column, which is 22 inches. You remember on this slide. See, just keep in mind this slide, the D's and all the things. Okay, the area of steel in first layer, in second layer, in third layer. See, this is 1, this is 2, this is 3. What will be the area of steel? Each and everything will be shown on the coming slides. So from this equation you are getting the I of column is 13,665 inch 4, and it is obtained by this thing. EC is equal to very famous equation. You are putting the values for concrete strength and it gives you 4415 ksi. For the column below level 2, EC into I column divided by length of column is this amount, okay, 355 into 10 power 3 inch cube. And for the column above level 2, see, this was below and this was above, EC will be equal to what is changed. A lot of things will be changed, but in this equation you can clearly see that E is constant, I is constant, only length of the column is changed, and here you are taking instead of 15 just 12. Okay, so you are getting the value for this term as 419 into 10 power 3 inch kip. For beams framing into the columns, so E for the beam you have calculated using this formula, and you know that apart from columns the FC prime was 4000, right? So E has changed. Similarly, I you have calculated it for the beams, and the length of the beam, you know, it was 24 feet span length, so you are getting 17 to 10 power 3 inch kip, where EB you calculated by this formula, IB you have calculated by this formula. Psi A is equal to what? You know this term. See, the column below level 2 and the column above level 2. Okay, and there was only one beam, so it is equal to 11. Psi A is equal to 11 and psi B is equal to 1. Column essentially fixed at base. Okay, if you go on the first slide, see, column is essentially fixed at the base. However, at this point you are taking the factor of this column as well and this beam as well, so this is psi A and this is psi B. Now using figure R625 from ACI 318, K is equal to 1.9 C, psi B is 1, right, and psi A is, you can see it, 11. So when you put a scale and draw a straight line, it will give you a k value where the line cuts this center line at a point. See, this is a log scale, this is 1, this is 1.5, and this is 2. So this is 1.6, 1.7, 1.8, and 1.9. So it is cutting it at a 1.9. So k is equal to 1.9. Okay, now KLU divided by R is equal to, you know the K value of K 1.9, you have determined the value of LU, you have determined the value of R, so it gives you a value of 47.87. It is greater than 22, so consider slenderness. Okay, you remember the flow chart. Okay, so here is cylinder column design where R is equal to radius of gyration. This is the formula. You obtain it by this or by 0.3 into C1, and from these two formulas the value is 6.35 inch. Okay, now we know that we have to design the column as a cylinder column. So coming to the method, which is moment magnification method. So moment magnification at ends of compression member. Compression member is column, right? A detailed calculation for load combination 4 gravity plus wind is shown below to illustrate the procedure. Table 3 summarizes the magnified moment computations for the exterior columns. Okay, M2 is equal to M2 north south plus sigma s M2s, where sigma s is the moment magnifier. Okay, as it's clear from with the name that the method is moment magnification method. So this sigma s is the moment magnifier, and it is one of these three values: 1 divided by 1 minus q, you remember the value of q, okay, or 1 divided by 1 minus summation of pu divided by 0.75 summation of pe. Now what are pu and pe? It's explained here. And the third one is second order elastic analysis. Okay, so for these three values are here. You have to check which one suits sigma s. However, a and c can also be used to calculate the moment magnifier. Okay, so these equation a and c can be used. In equation b, summation of pu is the summation of all factored vertical loads in the first story, because we are considering the first story column, and summation p is a summation of the critical buckling load for all sway resisting columns in the first story. Okay, pc is equal to, this is summation of pc, and pc is equal to pi square into ei effective divided by klu square. You know k, you know lu, you know e, you know I, and you know pi. So you can calculate pe, use summation of pe. You already know pu, you have calculated and used in determining the value of q. So you can find PE and you can put it over here, and you can find moment magnifier. Where EI effective, you have used EI effective here, right? So EI effective is either of these three equations. You can go through these equations. There are three options for calculating the effective flexural stiffness of cylinder concrete columns, EI effective. The second equation, this one, provides accurate representation of the reinforcement in the section and will be used in this example. Okay, so this equation is the accurate representation of column which we are considering, so we will be using this equation. Okay, I column, you know, c4 divided by 12, you know the value of c, 22 inches, so 19,521 inch 4, and ec is 4415. We already calculated it in step number 2. Beta ds is the ratio of maximum factored sustained shear within a story to the maximum factored shear in that story associated with the same load combination. So the maximum factored sustained shear in this example is equal to 0, leading to beta ds is equal to 0. So if this is 0, so ECI divided by 1 will be the final equation. Similarly, these terms will be 0. For exterior columns with one beam framing into them in the direction of analysis, there are 12 columns. Okay, with 8 reinforcement equally distributed on all sides and 22 by 22 inch column section, ISE is equal to 352.6 inch 4. EI effective from the equation 2 will be calculated 27.5 into 10 power 6 kip inch square. K, as we calculated previously, is 1.9. PC1 is equal to pi square into 27.5 into 10 square divided by this term, we already know it, is equal to 2933 kips. For exterior columns with two beams framing into them in the direction of analysis, there are 4 columns. Okay, there were 12 columns with one beams framing in them. Okay, and there are 4 columns with two beams. So psi A will be equal to columns stiffness divided by beam stiffness. You will get 5.5, and you know psi B is 1, as we already discussed, that essentially fixed at the base. So using again this chart for non-sway frames, we will get K. See, you join 1 with the 5.5 and it will cut this point at almost 1.71. So now your K is 1.71 for those exterior columns with two beams framing into them, okay, in the direction of analysis. So P2 is equal to pi square into these values. You know these values. This is the K value, this is the LU value. You get 3621 Kips. For interior columns, there are 8 columns. By the way, in this example, I'm just reproducing the values for these columns, but you don't need it, okay? You just need the exterior column if asked from you. So you have I column this EC of this. For the column below level 2, you will get this term as 503, and for the column above level 2, you will get 593. So for beams framing into the columns, you will get this term as 70. So you get all these three values. Just put it in psi A, you will get 7.8. See the values of columns, two columns, and two beams. So this is for the two beams framing into the column in the direction of analysis. So using these values 1 and 7.8, see this is 7.8, this is 1, just join them and you will get K of 1.81. Okay, this is for the interior column. Now with 8 number 8 reinforcement equally distributed on all sides and 24 by 24 inch column, ISE is equal to 439.1 inch 4, where this equation needs to be addressed. You know the value of this, it is 0. You know the value for all other values, the all other coefficients, for example zero point 0.2, you know EC, you know IG, you know ES, the elastic modulus of steel, you know ISE, you just calculated. And from this equation you got 37.1 into 10 power 6 kip inch square. Okay, so PE3 is equal to, you put it this value EI over here, and found out that 4372 kips is the value of PE3. Now summation of PE is equal to N1 into PE1 plus N2 into PE2 plus N3 into PE3. Summation of PE is equal to 12 into 2933. You calculated it, you calculated it, and you calculated it. For load combination 4, summation of PU is equal to 1.2 det plus 1.6 LR. You get this value. Now you know summation of PE, you know summation of PU. So sigma S is equal to, this is the magnification moment, okay, or moment magnifier, is equal to 1 divided by these values, and you know summation of PU, you know summation of PC. So just put the values summation of PC and summation of PU, and you get the magnifier value of 1.53, right? So you put the values for the top moment, and it will be 20.9 feet cape. M top second will be equal to M top NS plus magnifier into M top S. So the final moment is 62.7 kip feet. Okay, and for the bottom it is 168, and when you put it in equation the final is 189.7. So 62.7 and 189.7 feet kip are the top and bottom moments. You just find out that which one is the maximum and use it in a design. So here you get it. M second order effect is equal to maximum of M top second or M bottom second. Now M bottom second is equal to 189.7, and this is the maximum. Okay, so you choose the maximum one. So M2 for first order is equal to M bottom first order, which was 131.5 feet kip, right? And similarly for the minimum, you got the top one as a minimum, and for the first order the top one was 55.4 feet kip. So this is the difference in first order and second order moments. PU is equal to 722 kips. So a summary of the moment magnification factors and magnified moments for the exterior column for all load combinations using both equation options. For example, if you use the equation options to calculate EI effective, is provided in the table below for illustration and comparison purposes. Note that the designation of M1 and M2 is made based on the second order magnified moments and not based on the first order unmagnified moments. Okay. So these are the load combinations. These are 9 load combinations. They are explained here. The axial load values are provided. The moment magnifier is also provided. If you are using a CI 66444A equation, you get these magnifiers. And if you use the B, you get these magnifiers. So just multiplying the magnifiers with the moments, you get different values, okay, for M1 and M2. So I think it's enough to discuss till here in this video, and in the next video I will complete the design of this cylinder column. Okay, so see you in the next video. Thank you.